the test, right? I'll get those back next week. And I'd be happy to talk about the test as much as you want, but let's wait till I get it back so you have something to look at. Anybody have any homework questions or anything like that? Okay. So the last class was a week ago, and last time what we were doing was so we're now doing rigid body statics, and we did a problem where we had a object like this. There was a couple applied of negative 450. There was a force over here. There was a totally unknown force vector over here. I called this one F1, this one F2, and we knew the angles. And we used that as the about point. And we figured out what the forces F1 and F2 had to be for this to stay static. But the problem is, the next big step that we're going to take is when you see an object, like it doesn't look like this, but let's say that the body that we're trying to isolate is this arm here from this contraption. So you see the arm, you can measure the lengths and stuff, but what you don't see are those loads. There's stuff touching the outside of this, but you don't know that one of these is applying an unknown force vector, one's applying a force at a known direction, something's applying a couple, okay? All you know is that this rigid body here is connected to joints at the two ends, okay? And that's how, you'll normally go into problems. You'll see something in the world that's connected to joints, and you have to be able to make the step from seeing these joints to knowing what kind of loads those joints apply to a body. And so that's the next step we have to take, is talking about specific joint types and figuring out what kind of loads those joint types apply. The good news is a certain kind of joint always applies a certain profile of loads, and so we can always treat it the same way. So let's say, but that's not how problems arise. That's not how statics problems arise. Instead of being, given external loads, we're going to have to know what loads are applied to a body by a given joint. Okay. And we're first going to do this in 2 dimensions, and then in a little while we'll go to 3 dimensions. So first, joints, and we're going to start in 2D. And joints are connections between bodies. And all they do is limit the ability of one object to move relative to another one. Different joints do that in different ways. So they limit the relative motions allowed between bodies. And these restrictions on the motions are the key to understanding the loads they apply. Okay, so let's start out by imagining a rigid body that's like hovering in space, not touching anything, so not connected to any joints. Um, so imagine a hovering rigid body in 2D. So we're starting out in 2D, so this thing can only move in a plane. Not touching its surroundings. Okay, so this is a arbitrary thing, and it's just floating there in space. It is rigid, so it's not bending or anything. But it has three motions that it can make. And these motions we're going to call degrees of freedom. It can move along an axis. Okay, so choose an axis. So let's choose our axis like this, and this object can move in the positive direction along that axis or the negative direction along that axis, right? But it's free to move, so it doesn't have, its motion isn't confined to that axis. So it can also move along an axis perpendicular to that first one. So it can move along an axis perpendicular to the first axis. And notice that with those two things together, if it can do both of those at the same time, it can move anywhere in space. Okay, but we haven't talked yet about this thing changing orientation, and it can change orientation. So it can rotate in the plane. So all this together says unrestricted bodies in 2D have 3 degrees of freedom. And those are 2 translational and 1 rotational. Okay. The only way to take away a body's ability to move in all these 3 ways let's say the only way to restrict this object's motion is to apply loads when it tries to move. So first, to stop motion along an axis, something must apply a force that's parallel to that axis. To stop motion along the perpendicular axis, something must apply a force along that perpendicular axis. And to stop a rotation, something must apply a couple to this object. A couple is what fights. So if I start leaning forward, I'm not going to do it because I fall. But the way to keep me from rotating down and smashing my face on the ground is to apply a couple to me, and there's a lot of ways you can do that. But like if I lean forward, like, oh, remember that Michael Jackson video where he has the shoes on and he like leans forward? So he leans way over. The thing that keeps him from tipping over on his face is something's applying a couple to him that keeps him rotated. Okay. And so to prevent translations, you apply forces. To prevent rotations, you apply couples. To stop a rotation, must apply a couple. Now we're in 2D, so there's only one axis where you can apply couples. That's going to change when we get to 3D. And so for each joint that we're going to talk about, I think there's 6 total. For each joint type, ask yourself, which degrees of freedom are prevented, restricted, that tells you what type of load or loads joint applies. Okay, let's just go through a list of the ones that we're going to see a lot, and we'll sort of think through it together. And I'm going to break it down into 3 different categories. So joint category 1, I'm going to call it. These apply one force in a known direction and therefore introduce one variable into your equations. So one variable into, let's say, into Newton's laws. The first one of these is contact without friction. We've already seen this in particle statics. And this would appear something like this. So there's the ground or another body. And there's part of the body that you're analyzing. Let's say that this is body 1 and this is body 2. So let's think in this case, I don't have a model of this one, but in what way is motion restricted by this contact? So if this body 1 was just hovering in space, it could translate anywhere and it could rotate anywhere. Okay. But because it's in contact with the ground, it can't translate perpendicular to the ground. Okay. Well, it could translate up, and I'll talk about that in a second. But let's just think of it as being totally confined to move parallel to that surface. Okay. So it can't move this way. It can move this way. Can it rotate? Yeah, I mean, you could take the end of this and rotate it, right? So it doesn't prevent rotation. It doesn't prevent motion along the ground. It does prevent translation into the ground. So what's the direction of the load? You know, what load does this joint apply? We've already seen what it is before. Yeah, it applies a normal force. It applies a force perpendicular to that surface that prevents this from moving into the surface. If this thing tries to sink into the surface, the ground fights against it to keep it from doing that. You follow what I'm saying about how it comes from the restrictions that the joint makes that determine what loads are applied? Okay, so let's think of what the free body diagrams look like for these two bodies. So free body diagram for body 1. That's not what it look like. Okay, and the ground was at an angle like this. And so the force has to be perpendicular to that. We happen to know this is a pushing contact, so it has to be toward the chosen body. And I'll represent that with a variable r. So this has to be perpendicular to the surface. And if you wanted to draw a free body diagram of body 2, it would be equal and opposite because of Newton's third law. So this would also be r. And so when I said that all of these in joint category 1 introduce one variable into Newton's laws, the variable here is r. There's no way to get around having an unknown variable r put into your equations. And that r is going to be whatever is required for this thing not to be accelerating. If anyone has any questions about these, feel free to ask. Notice that for contact without friction, so R is always positive because the force is always toward the chosen body. So we know that direction. So if you ever do a problem like this and you draw your R like that and then you go through the calculations and you get an R value that's negative, you know something went wrong because an R value that's negative would say that the ground is pulling on that object and a frictionless contact can't pull. So either the thing is designed wrong or you made a calculation error. Okay, the second thing is a roller. So this is still in joint category 1. And this can be drawn a couple of ways. So you can, sometimes you'll see this as like just like a little wheel or a little ball or a little rolling pin or whatever between the body and the ground or between the two bodies. So let's say this is body 1, this is body 2. Or sometimes you see it like this. It looks sort of like a little roller skate connecting the two things. Those mean the same thing and you treat them the same way. So body 1, body 2. And it works exactly the same way as a frictionless contact. In fact, sometimes if you have a frictionless contact, people draw it as a roller, just make it clear that there's no friction. And it all works the same way. This object can't sink into the ground because the roller is holding it there. It can roll this way or that way. It can roll parallel to the axis, the surface, and it can rotate. Okay. Now, the way I have it drawn here, it can only rotate 2 degrees or something before this hit the ground. But we only care about the orientation that we're looking at that instant, So if we're looking at this in this instant, then as far as we're concerned, this is totally free to rotate. You know what I mean? Because it has room enough to rotate a little. Free-body diagrams. So for body 1, it would be perpendicular to the surface. For body 2, it would be equal and opposite. And then the third one is a pin and slot joint. And that looks something like this. So you have one body with a pin going through it, and that pin can slide in a slot. And that connects it to another body. So this is body 1, and this is body 2. And I have a little model of this one. So the way I have it drawn there, so this right now is in the orientation that's shown. You see that? And so what motions are allowed and what motions are not allowed. It's free to translate along the slot, but it's not free to translate perpendicular to the slot. The connection between the pin and the slot stops that, and it's free to rotate. Okay, so again, there's a force applied perpendicular to the slot, but no force parallel to the slot and no couple. Anybody have any questions about that, or anyone want to look at this more closely? Does that make good sense? I think one of my little pins broke off. I need to print another one of these. Oh, one thing before I draw these, the roller has the same thing going on that the frictionless contact did. So notice R has to be positive here too. Because just like frictionless contact, rollers can't pull the thing back if it tries to jump off the ground. Okay. Okay, so the pin and slot joint, free body diagram of body 1. So there's body 1. The slot is like this. And the force has to be perpendicular to the slot. So I'll call this force R. These have to be perpendicular. And free body diagram of body 2. That force has to be equal and opposite. So it's like that. So while you're putting together the equations, a pin and a slot, a roller, and a frictionless contact are all the same. There's one difference though with a pin and slot joint, and that is that this slot doesn't have the equivalent of a thing being able to jump off the ground with frictionless contact. So if it's oriented like this, okay, if this thing tries to push into, in this direction, the slot stops that from happening. And in this case, if it tries to move in this direction, the slot stops that from happening. So for the pin and slot, that R can be positive or negative. So it can be positive or negative. Any questions about any of these yet? Okay, so that's all that first category. Those are the ones that apply one force, and so they introduce one variable. Now we're going to joint category 2. And these are the ones that apply forces in 2 directions, force components in 2 directions. And so they introduced two variables into Newton's laws. And there are two of these. The first one is a pin joint. And this will look something like this. So there's like a hinge connecting those two bodies, and it's the two bodies are free to move along that hinge. I'll call this body 1 and this body 2. And so here's a one. So here it is in the orientation that's shown there. So pick any axis you want. It doesn't matter what you pick. You still, and I'm going to hold the bottom one still and see if I can move the top one. I can't move the top one. I can't make it translate in the direction of whatever axis I choose. Say I choose this one. I can't move it in that direction or it's negative. And I also can't move it perpendicular to that axis or the other direction perpendicular to that axis. Okay? So all translation at that point is totally stopped. Okay? And so I can represent that as this joint applies a fully unknown force vector to either one of those bodies that you're looking at. It doesn't apply a couple because it's still free to rotate. Okay, so in a free body diagram, there's an unknown force vector but no couple. Right? Any questions about that? Anybody need a knee replacement? I'll sell this cheap. You're gonna have to go easy on it. Okay, well, if you're embarrassed to say it in front of the class, come talk to me after. Okay, so free body diagram of body 1. We'd represent this the way we represent, unknown force vectors. So I'll call this force on 1, I2. And those are just in the direction of your coordinate axes. There's no preferred directions here. And so the variables that would be introduced into Newton's laws would be F12x and F12y. And then the free body diagram of body 2 is F on 2 by 1, and Newton's third law says that's negative F12. And then second, can you remember what's the joint that we used for particle statics that applies an unknown force vector like that? That's right, contact with friction, exactly. So friction contact. So the way that would be drawn in a problem is exactly the way frictionless contact would be drawn. It's just the problem would say that there's friction at that point. again, so this is body one, this is body two. Body one is free to rotate, but it can't sink into the surface, and it can't slide along the surface because of the friction. So a free body diagram of body one would have F12, and a free body diagram of body two would have F21, which is equal to negative F12. So we had the first category that restricted one of the 3 degrees of freedom. The second category restricted 2 of the degrees of freedom. The only thing left is something that restricts every kind of motion. And so joint category 3 only has one member. And this applies 2 force components and a couple. And that means that it introduces 3 variables into Newton's laws. And the only thing that meets that requirement is what's called a fixed joint, or sometimes people call it a weld joint, I guess, if it's metal. And that would be drawn something like this. Yes. So I'll call this body 1, this body 2. A free body diagram of body 1 would have the force vector F on 1/2 and a couple M12. And free body diagram on body 2 would have a force vector F on 2/1, which is equal to negative F12. And the couple M on 2/1, which is negative M12. I didn't say specifically that that for couples that Newton's third law idea applies, but if you think of what a couple is, it makes sense that it has to. Remember, a couple is 2 equal and opposite forces, and so acting at a distance. And so if body 1 is applying a force this way and a force this way to body 2, body 2 is applying a force this way and this way to body 1, and it works out the same way. Okay. Any questions about any of those? Okay, so those are the only kinds of forces we're going to have to deal with for 2-dimensional problems. And we'll do a few of those, and then we'll talk about how to treat joints in 3 dimensions. The thinking's exactly the same. It's just a little harder to think through it, 3-dimensionally. Okay, so let's say that there's a wall over here, and a beam is connected to the wall with a fixed joint. And let's say this angle is 50 degrees. And there's a cable connected to this beam that goes over a pulley. And hanging from the other end of that cable is a mass of 200 kilograms. And we want to know, what are the reaction loads at the wall? And you can imagine, doing problems very similar to this for engineering applications, especially like civil engineering kind of things. It's easy to imagine. If you have a beam like this in your structure that you know what it's going to have to support, then you're going to have to calculate how strong this connection has to be there, and that's what we're going to do. We're going to calculate the forces that the wall has to apply to this thing to keep it static. Okay. So start with a free body diagram of the beam. Do we know the force that the cable, it should have a mass too, and it needs to have a length. Okay, so the length is 2 meters. And the mass is 100 kilograms. Without doing a calculation, do we know what the force is that cable is going to apply to the beam? Well, yeah. So if it doesn't occur to you right away, then the thing to do is draw a Freebody diagram of the mass, calculate the tension in the cable, which then it's just going to be equal to 200 times 9.81. And then since it's all one cable, that's the force that has to be applied here. So I'm going to skip the step of isolating the mass, but you can always do that. So it's an upward force of 200 times 9.81 is 1962. The weight of an object always acts at its center of mass. So there's a downward force of 100 times 9.81, so 981. And then the only other place where the surroundings make contact with this is at the fixed joint. So we have a reaction force there. I'm not going to bother to use the subscript notation because we're not going to isolate the wall in this case. And a couple that I'm going to call M. R for reaction. Maybe I'll call this MR for reaction moment. Any questions about that yet? And I'm going to use just a standard coordinate system. So now I'm going to fill out the table. So row vector, force vector, moments. And one of these loads, each one of these loads gets its own row in the table. So the first one, let's use the cable force. So that's the 1962. And before we start filling this out, we have to choose an about point. Anybody have an idea for an about point? You can put it anywhere, and the answers you get will be the same. You can save yourself a little bit of math if you put the about point at the place with the most unknown forces, because then you don't have to calculate the moments produced by those, because any force happening at your about point produces 0 moment. So I'm going to put the about point here. Okay. So what's the row vector? How would we calculate the row vector for the 1962? So what we're looking for is this vector. Where this angle is 50 degrees and this length is 2. So that's going to be 2 times cosine and sine 220 degrees, which is cosine and sine of 220 degrees is negative 0.766, negative 0.643 times 2 is 2 times negative 0.666 is 1532. Is that right? 1.532. Anyone have a calculator? Negative, and this one is negative 1.286. 0 for Z. Okay. Yes. And then the force, that's in the positive y direction. So 0, positive 1962, 0. And now we need the cross product. So I can't do that one. Negative 1.532 times 1962. Times 1962. Okay. Any questions about how I got that stuff? And now we'll go to the weight force. Well, the row vector for that is just going to be half of the last row vector. You see that? So that's going to be 0.766 negative 0.643, and then 0 for Z. And the weight force is 0, negative 981, 0. And so what's 0.766 times 981? 751.4 in the Z direction. And now we're down to that reaction force. This is in a plane, so there's only x and y components for r. So rx, sorry, I'm putting that wrong. Well, this is the reason that we chose the about point here. What's the row vector for that force r? 0, because they're at the same place. The force vector is rx, ry, 0. And so the moment is 0, 0, 0. And now the last one is the couple. For couples, we don't care about the row vector, and we don't care about the force because the equal and opposite forces cancel. And so all we have here is 0, 0, mr. That's just the pure couple, pure moment. And notice that you're never going to have any z components on your forces, so we can forget about these. And you're only going to have z components on your moments, so you can forget about these, these, and these. And now we'll put this stuff into Newton's laws. So first, Newton's second law says, and now I'm just going straight down that column and adding up all of those vectors. 0, 1962, plus 0, negative 981, plus rx, ry is equal to 0s. And now the moment equation, rotational Newton's second law. I'm going to add up all the z components because we're in the plane. So we have negative 3790.6. Positive 751.4. Zero plus mr is equal to 0. And so now you have two equations for for Newton's second law that says Rx is equal to 0 and Ry is equal to negative 981. You know, just solve the algebra. That's in Newton's. And rotational Newton's second law. What's 3790.6 minus 751.4? Wait, what? Oh, 3039.2. That's our MR, and that's in Newton meters. Okay, so what this says is for this system to stay at rest, the wall has to provide a downward force on this of 981. Okay, and that's to counteract the, well, so there's weight in there, whatever, but you know, that's to keep this from pulling it straight up. And it also has to apply a couple. Is this couple clockwise or counterclockwise that the wall has to apply? Counterclockwise because it's positive. And so does it make sense if you look at this system that the wall has to apply a counterclockwise moment to counteract it? Yeah, if this if this pulled it freely here, this thing would, start to rotate that way. And so to counteract that, the wall has to pull it that way. And you can use a calculation like that to, figure out like what kind of weld you need to do, what kind of materials you need. Any questions about that one? Okay, let's do another one. Okay, so let's say we have a horizontal beam that's connected to the wall over here by a pin joint. So it's free to rotate along this. And then it has another pin in the middle that's free to slide along this slot. And angle of the slot with the horizontal is 45 degrees. Let's say that the mass of this thing is 50 kilograms. There's a downward force at the end of 1,000 newtons. And the length, let's say the length of this beam is 1 meter. What are the reaction loads at the joints? Okay, so first, free body diagram of the beam. There's a weight force in the middle. I said it was 50 kilograms, so this is 50 times 9.81, so 490.5. And then there's the 1,000 Newton force over here. At the left end is a pin joint. So what kind of loads are applied by a pin joint? Yeah, all transition is stopped, but it can still rotate. So this is an unknown force vector. So I'll call that R. And then there's one more joint, the pin and slot joint. What do we know about that force? Yep, and it's perpendicular to the slot. So if the slot is like this, that force has to be perpendicular, and you can draw it either direction. So I'll do it like that, and I'll call this F. Any questions about that? Okay. So the table, row, force, moment. And where do you want to put the about point? I think the center or the left end are both good enough choices. I guess I'll put it over at the left end. Okay, so now we'll go through these loads one by one. First is the R force vector. What's the row vector for that? Yep. And the components, there's an X and a Y, but no Z, because we're in the plane. And the cross product is zeros. The next one is the weight force. What's the row vector for that? Yep. Remember, the row vector goes from the about point to where the force is applied. So this is 0.5, 0, 0. The force is 0, negative 490.5, 0. And the cross product is 0, 0, negative 245.25. And now that force F, what's the row vector for that? Same, yep, it's in the same spot, so it's the same vector from the about point to there. So this is 0.5, 0, 0. This angle, that's F times cosine and sine of 135, yep. So that's negative 0.7071 F, positive 0.7071 F, 0. And the cross product is 0.3535 F. And then the last one is the 1,000 Newton force. What's the row vector for that force? Yep, good. 1, 0, 0. The force is 0, negative 1,000, 0. And the cross product is negative 1,000. And again, you can see like in 2D, it doesn't even, there's no reason to even write these extra components. They never come up. So Newton's second law, add up all the forces in the force column. So we have Rx, Ry, plus 0, negative 490.5, plus negative 0.7071 F, positive 0.7071 F, plus 0, negative 1,000 is equal to zeros. And then the moment equation says negative 245.25 plus 0.3535F minus 1,000 is equal to 0. And so can someone calculate what F is? From the moment equation? Okay. And then, so Rx is 0.7071 times that. Okay. And then Ry is 1490.5 minus 0.7071 times F. $24? Oh, okay, 1,000. It's probably just 1,000, and that's like round off error from the signs, the sine and cosine. Okay, so that force vector R is 2490.9 negative 1,000.5 newtons. The force vector, that pin and slot joint, is 3522.6. So you wouldn't know this from just glancing at this. It's hard to have intuition about stuff like this, but that pin in the pin and slot joint has to take a lot more force than the pin over here on the left end. And that's the kind of thing you could use as a design consideration, like, oh, I don't want that. I want to even it out more. Maybe I need to change the length of this over here or whatever. Any questions about that? Okay. So if you're ready to leave your binder, you can put it up here. Yes. Yeah. And if you're not ready to leave it, you can bring it next week. That's fine with me. And have a good weekend.